Thank you. So today I'm going to talk about a problem in fair division that is called consensus halving. This is joint work with Aris, Filos-Ratsikas, Katerina, Sotiraki, and Manolis, Zampetakis. So let's dive right into it. In this fair division problem, we have a divisible resource, which we model as the interval 0, 1. This is the usual way divisible resources are modeled in the cake cutting literature, for example. And I might also refer to this interval as a cake sometimes during the talk. Obviously, it doesn't have to be a cake. It can be any divisible resource which can reasonably be modeled as a segment. So we have this divisible resource and we have n agents that have valuations over this segment. For this talk, we're going to assume that all the valuations are piecewise constant. Let me explain a bit what I mean by that. So for any agent, there is an underlying density function that is piecewise constant. In other words, a step function, and that gives rise to the valuation of the agent. The easiest way to think about it here in those pictures is if you look at the blue agent, for example. I've drawn the density function for that blue agent, which is indeed piecewise constant. And if you want to find out what value does the agent have for some subset of the interval, then you just have to look at how much volume corresponds to that subset, and that gives you the value. So the fair division we consider here is called consensus halving. It has been studied since the 1940s or so, under various different names, but it's always the same problem, which is the following. So we want to partition the divisible resource, the interval, into two parts, such that all the agents agree that we have cut it in half. What do I mean? That the two parts have the same value. So formally, for any agent I, the value of the one half, which is I plus, should be the same as the value of the other part, I minus. These parts don't have to be contiguous. So I plus can be made out of multiple intervals. It can be a union of many intervals. The only important thing is that we're partitioning the cake into two parts. Let's, hence the name consensus halving. Let's take a look at some examples. So the first example is very simple. The agents have just a single block of value. You can think of this as being that every agent just cares about some subinterval of the cake and has uniform value over that. So in this case, all the agents actually have the same valuation function. And it's very easy to construct a consensus halving here. Just put a cut through the middle of the blocks. Let the left half be I plus, the right half be I minus. And it's easy to see that the value of the two is equal for all agents. In the left part, you have half a blue block. In the right part, you have half a blue block, and the same for all the other colors as well. So indeed, all the agents will agree that I have cut the cake in half. Let's look at a slightly more complicated example. Let's say I put a cut over here. So now clearly the green agent would be happy with that. There's half of his block on one side, half of his block on the other side. The blue agent is also going to be happy with this because there's half his value on one side and half his value on the other side. But the red agent will complain because there's more value on the left than on the right. But it's easy to fix in this case. If we just add a cut over here and let I plus be the left interval and together with the right interval, so the union of these two intervals, and we let I minus be the interval at the center. And now it's easy to see that all the agents are happy with this consensus halving because even the red agent now has the same amount of value in I plus and in I minus. So here we had to use two cuts. Can it get worse than this? Yes, so I claim that in the following example, which has three agents, we actually have to use three cuts. And the reason for this is that if some block does not contain a cut, then there's no way that it is a consensus halving. Consider, for example, the first block, the blue block. If the blue block does not contain a cut, then the whole block has to be in I plus, or the whole block has to be in I minus. In both cases, the blue agent is not going to be happy. So there needs to be a cut in the blue block, and the same argument also tells you that there needs to be a cut in the green block and in the red block. And if you do that, if you put it to the middle of the blocks, then it's easy to see that we can indeed obtain a solution. Now, this example was for three agents. But the same argument can be generalized to n agents by simply having every agent value a separate disjoint, non-overlapping block of value. And in that case, we will have n agents, and we will need n cuts to solve it. So can it get any worse with n agents? Is it possible that we might need more cuts? The answer is no. So the consensus-halving theorem tells us that whatever the valuations, there always exists a consensus halving that uses at most n cuts, where n is the number of agents. This theorem is also known as the Hobby-Rice theorem because it was first proved by Hobby and Rice in 1965. And it was proved again by Simmons and Su in 2003 with a different proof and a strengthening as well. And Simmons and Su are also the ones that came up with this name for this problem, consensus halving. By the way, this theorem actually holds for very general valuations, not just the ones we consider here, not just piecewise constants. So it's a pretty strong theorem. And the proof relies on using a tool from topological fixed point theorems. The theorem is called the Borsuk-Ulam theorem, which is quite famous and has a lot of applications. I won't say more about it here, but the name of the theorem will make some appearances in the rest of the talk. So this is the mathematical existence theorem, but we are computer scientists, so obviously we care about the computational aspect of this problem. So for the rest of this talk, the computational model that we're going to consider is that the valuation functions, which are piecewise constant, are given explicitly in the input. This means that we have full information about the valuations. There's nothing hidden about them. There's nothing hard to obtain about them. We know everything about the valuations. Now, what is a reasonable question to ask regarding this consensus halving problem? We could ask for a consensus halving that uses the minimum number of cuts. So recall that depending on the instance, we might need more or less cuts to achieve a consensus halving. So we can ask for a solution that uses the least number of cuts for this instance. However, it turns out that this problem is NP hard, as was shown by Filos-Ratsikas, Frederiksen, Goldberg, and Zhang. So we're probably asking for too much here. What is a more reasonable question then? Let's compute any consensus halving that uses at most n cuts. By the consensus-halving theorem, we know that such a consensus halving necessarily exists. So it's a reasonable question to ask the algorithm to just return any such consensus halving, which uses a reasonable number of cuts, n. So for the rest of this talk, this is the problem that we will consider, and I will refer to this problem as the consensus halving problem. Now, the interesting thing about this problem is that it turns out that it cannot be NP hard unless NP equals co-NP. And the reason for this is that the consensus halving problem lies in a complexity class that is called TFNP. So let me tell you a bit about this. This class was defined by Megiddo and Papadimitriou in 1991, and it contains all total NP search problems. Let me parse that sentence. So these are search problems, which means we're looking for a solution, not for a yes/no answer. It's not a decision problem. Then the problem should be in NP in the following sense. If I give you a candidate solution, you should be able to check in polynomial time that it is indeed a solution. And finally, the problem should be total, which means that for any instance, there should always exist at least one solution. It's easy to check that the consensus halving problem indeed has those three properties, and thus it is a problem in TFNP. Now, showing that a problem in TFNP is hard, or rather giving evidence of intractability, is tricky for two reasons. The first reason is that if you show that some TFNP problem is NP hard, then this immediately implies that NP equals co-NP. That was proved by Megiddo and Papadimitriou in their original paper. Since we don't believe that NP equals co-NP is likely to hold, that means that NP hardness is not really a tool that we can use here. Now you might think, maybe let's show TFNP hardness then. Maybe NP hardness is too much. The problem is that it is believed that there's no TFNP complete problems because of the way TFNP is defined. And even if there are, we don't know any. So this doesn't seem like a viable option. So what can we do? How can we give evidence that a problem in TFNP is intractable? Papadimitriou proposed to look inside TFNP to investigate its inner structure, to define a hierarchy of subclasses, to classify problems in those subclasses, to then be able to make statements of the form, oh, if this problem is solved in polynomial time, then a bunch of other problems will have to be solvable in polynomial time as well. So you might have heard of PPAD or PLS. I've put some of the classes here. Obviously, there's much more. Let me add some complete problems. So for PPAD, for example, we know that computing a Nash equilibrium is PPAD complete. For the class PLS, we know that computing a local max cut is PLS complete, and various other local search problems are PLS complete. And for the class PPA, which is a more obscure class, less well known, we know that computing a Borsig-Ulam fixed point is PPA complete. Now, recall that the Consensus-Halving Theorem was proved using the Borsig-Ulam theorem, and in fact, this proof can be turned into a polynomial time reduction to show that the consensus-halving problem actually lies in PPA. Now, the surprising result that was obtained relatively recently is that this consensus-halving problem is actually complete for this class PPA, for this model with the piecewise-constant valuations that were shown by Filos-Ratsikas and Goldberg. And their hardness result even holds for some relaxations of the problem, namely, first of all, for the approximate consensus-halving problem, which is usually called the epsilon consensus-halving problem. So in that problem, instead of requiring that all the agents believe that the value of I plus is the same as the value of I minus, we relax this by saying the discrepancy between the two values should be at most epsilon, an additive error of epsilon. And for this to make sense, we assume that all the valuations are normalized, namely that for any agent, the value of the whole cake is 1. And the second relaxation for which the hardness still holds is if we allow extra cuts. So instead of the n cuts, we allow n plus k cuts for any constant k. So this is a pretty nice hardness result, but let's talk a bit about what it actually means. What does it mean that the problem is PPA complete? So first of all, from a mathematical standpoint, it means that the consensus-halving theorem is equivalent to the Borsig-Ulam theorem. Namely, you can prove the Borsig-Ulam theorem by using the consensus-halving theorem. And in fact, the connection is stronger, namely, it holds under polynomial time reductions. And from a more computational perspective, it means that we are unlike the consensus-halving problem is unlikely to admit a polynomial time algorithm. Why is that? So we know that the problem is PPA hard, which means that in particular it's PPAD hard. And so that means that it's at least as hard as finding a Nash equilibrium, for example. So if we believe that a Nash equilibrium is a hard problem, then so should this problem be as well. Let's take a closer look at this hardness result. So it holds for piecewise constant valuations, as I mentioned. And the thing is that these valuations can be pretty complicated. This is an example of what this reduction does, what kind of agent gadgets it uses. So agents can have a polynomial number of blocks of value, and the blocks can have different heights. So maybe the problem is hard just because we're able to construct these weird gadgets. Maybe the problem is easier if we only consider simpler valuations. So what if, for example, every agent is allowed to have at most a constant number of blocks? Or what if, for any agent, the height of all the blocks has to be the same? Is the problem solvable in polynomial time then? So this is what we set out to answer in this project. And unfortunately, the answer is no. So what we show is that the consensus-halving problem remains PPA complete, even if all the agents have 2-block uniform valuations. Let me explain what I mean by 2-block uniform valuations. So every agent has at most 2 blocks of value, and the 2 blocks have to have the same height. Another way to think about it is every agent values at most two sub-intervals of the cake and values them uniformly. So these are all examples of 2-block uniform valuations. And again, the hardness holds even for the approximate version of the problem. It holds even if we allow extra cuts, where we have a slight strengthening. And quite interestingly, the proof is actually simpler. We are able to significantly simplify the proof. The original proof was around 40 pages, and our proof fits in 10 pages. So we think this is also an important contribution here, even though the result is strong in that the proof is much simpler and easier to understand. So what does that mean? The problem is hard. Is there any way to make the valuations any simpler than this? And yes, of course there is. We can consider single block valuations where every agent just values a single block of value, like in this picture. And then we can ask the question, is this polynomial time? Is it still PPA complete? Is it PPA complete maybe? Or is it complete for some other class? And the very surprising answer here is that we don't know. We don't know what happens in this simple case, but we do provide some positive results for some special cases. So we show that the consensus halving problem, if all agents have single block valuations, can be solved in polynomial time in 3 special cases. The first case is if epsilon is equal to 1/2. Recall what this means, that any agent is okay if they see a disparity of 1/2, namely if they see that I plus has value 1/4 and I minus has value 3/4, that would still be fine for them, barely. And this is achieved by a greedy algorithm, but the details are quite tricky already. It's not trivial, and that's why we only obtain 1/2 and not something better here. The second case that we can solve is if instead of n cuts, we allow 2n minus k cuts for any constant k. And this is obtained by solving a polynomial number of LPs. In fact, you can solve the problem exactly here. And the final case that we can solve is if the so-called maximum overlap number is constant. What is the maximum overlap number? It's for any point on the cake, the maximum number of agents that have a value at that point, and you might take the maximum over the whole cake. Let me explain with a picture. So in this example, the maximum overlap number is 2, because there is a point where the green agent and the blue agent have value, 2 agents, but there's no point where all 3 agents have value. And so if this maximum overlap number is constant, then we can solve the problem in polynomial time by using a dynamic programming approach. Okay, let me finish this talk by mentioning some open problems. So obviously, the main open problem here is what happens with a single block case. It seems very simple, but we don't know how to solve it, which is quite surprising. And then the second open problem is if you consider a generalization of the consensus halving problem, where you don't want to partition into 2 parts, but you want to partition into p parts instead. And again, you want every agent to agree that all the parts have the same value. And this problem is called the consensus 1/p division problem. And what we know, so first of all, from another project with the same authors, we know that this problem lies in a class that's called PPA-P, which is another version of PPA, basically. And in this paper, we also showed that consensus 1/3 division is PPA-D hard. And that's basically all we know to the best of our knowledge about this problem. So it's wide open. There's a lot of stuff to show. All right, that's it. Thank you for your attention.